The method of factorization, splitting the middle term. Welcome, everyone. Before we dive into today's new technique, let's take a moment to recap what we have already learned. In our previous lessons, we established that when we talk about the roots of a quadratic equation, we are simply looking for those specific values of x that make the entire equation true, essentially, the values that make the equation equal to 0. Now, as we move forward, you will find that solving these equations can sometimes be tricky. That is why one of the most efficient and powerful tools in your mathematical toolkit is a method called factorization. So, what exactly does factorization involve? Think of it as the process of breaking down a complex quadratic polynomial into a much simpler form, a product of two linear expressions, which we often call binomials. The real beauty of this method becomes clear when we reach our goal. When we can rewrite a quadratic equation as a product of these two factors set equal to 0, it becomes much easier to determine the values of x that satisfy the equation. In the next few slides, I will show you exactly how to perform this splitting technique step by step. The conceptual logic. Now that we understand that factorization is a powerful tool for finding the roots of a quadratic equation, let's look at the underlying logic of how this process actually works. First, let's recall the standard form of a general quadratic equation, which is x squared plus bx plus c equals 0. Our ultimate goal here is to take this three-term expression, known as a trinomial, and transform it into a different form, a product of two simpler linear brackets, specifically px plus q, all multiplied by rx plus s, which equals 0. To bridge the gap between the standard form and this factored form, we use a specific technique called splitting the middle term. As you will see in the next few slides, the core of this method lies in a very specific mathematical goal. We want to take that middle term, bx, and break it into two separate parts, which we will call px and qx. However, we can't just pick any two numbers. For the factorization to be mathematically valid, these two new coefficients, p and q, must satisfy two strict conditions. First, when you add them together, their sum must be exactly equal to the original middle coefficient, b. And second, when you multiply them together, their product must be equal to the product of the coefficient of the x squared term and the constant term, in other words, a times c. Mastering this relationship is the secret sauce to solving almost any quadratic equation using this method. Step-by-step pedagogical approach. Now that we understand the conceptual logic behind why we want to split the middle term, let's walk through the actual procedure. I want you to follow along closely, as this is a systematic 6-step process that you can apply to almost any quadratic equation. Step 1 is all about the standard form. Before you do any math, look at your equation. It must be written in the form x squared plus b x plus c equals 0. If you see any numbers or terms sitting on the right-hand side of the equals sign, move them over to the left by performing the opposite operation. We need everything on one side so we can clearly see our coefficients. Step 2 is to identify your coefficients. Once the equation is in standard form, clearly label your values. Find the value of a, which is the coefficient attached to x squared, find b, the coefficient of x, and find c, which is your constant term. Step 3 is often the most critical part of the process, finding the product and the sum. First, calculate the product of a and c. Now, your mission is to find two specific numbers. Let's call them p and q. These two numbers must satisfy two strict conditions. When you add them together, the sum must equal b. And when you multiply them together, the product must equal the value of a times c that you just calculated. Step 4 is where we actually split the middle term. Instead of writing the middle term as b times x, you are going to rewrite the equation using the two new numbers you found. You'll replace b, x, with p, x plus q. X. This expands your trinomial into a 4-term polynomial, which is exactly what we need for the next step. Step 5 is to factor by grouping. Now that you have 4 terms, split them down the middle into 2 pairs. Group the first 2 terms together and group the last 2 terms together. From each of these pairs, look for the greatest common factor, or GCF, and factor it out. You should see something like a x squared plus p x grouped separately from q x plus c. Finally, step 6 is to extract the common binomial. If you have done the previous steps correctly, you should notice that a common binomial factor has appeared in both groups. You will factor this common binomial out, leaving you with the final product of two linear factors, which looks like p x plus q all multiplied by r x plus s equals 0. Once you reach this stage, you have successfully factorized the quadratic. Illustrative examples. Now that we have understood the theory and the step-by-step logic behind splitting the middle term, let's put it into our first concrete example. We are looking at a pure algebraic equation, x squared plus 5x plus 6 equals 0. To solve this, let's follow the systematic approach I just outlined in the previous slide. First, we need to identify our coefficients. Looking at our equation, we can see that A equals 1, B equals 5, and C equals 6. Next, we move to the most critical part. Finding our two magic numbers, P and Q as we discussed, we need two numbers that satisfy two conditions. First, their product, which is a times C, must be 1 times 6, which equals 6. Second, their sum must be equal to our middle coefficient, B, which is 5. If we look at the factors of 6, we can see that the two numbers that multiply to 6 and add up to 5 are 2 and 3. Now, we perform the actual splitting of the middle term. We will replace the 5x in our original equation with 2x plus 3x. This transforms our trinomial into a 4-term polynomial. X squared plus 2x plus 3x plus 6 equals 0. With the middle term split, we can now proceed to factor by grouping, just as we planned in our step-by-step guide. Let's group the first two terms together and the last two terms together. This gives us the quantity x squared plus 2x plus the quantity 3x plus 6, all equaling 0. From the first group, we can factor out the greatest common factor, which is x, leaving us with x times the quantity x plus 2. From the second group, we can factor out a 3, leaving us with 3 times the quantity x plus 2. Notice something very important here. Both groups now share a common binomial factor, which is the quantity x plus 2. This is exactly what we want to see. Finally, we extract this common binomial to arrive at our final factorized form. The quantity x plus 2 multiplied by the quantity x plus 3 equals 0. This completes the algebraic process. In the next slide, I will show you how we can apply this exact same logic to solve a more complex, real-world geometry problem. Illustrative examples. Now that we have mastered the algebraic theory in the previous slides, let's see how we can apply this method to a practical, real-world scenario. This is example 2, which focuses on a geometry application. Imagine you are designing a rectangular garden. We are told that the total area of this garden is 40 square meters, and there is a specific relationship between its dimensions. The length is 3 meters more than the width. Our goal is to find the actual dimensions of this garden. Let's walk through the step-by-step solution together. First, we need to formulate our equation. To do this, let's assign a variable to our unknown. Let the width be x meters. Since the length is 3 meters more than the width, we can represent the length as the quantity x plus 3 meters. Now, recalling our area formula, area equals length times width. So, we set up the equation as x multiplied by the quantity x plus 3 equals 40. When we expand this, we get x squared plus 3x equals 40. To use the method we've been learning, we must have the equation in standard form equal to 0. So we subtract 40 from both sides, giving us x squared plus 3x minus 40 equals 0. Next, we identify our coefficients. Looking at our equation, A is 1, B is 3, and C is negative 40. Now, we move to the most critical part of the process. Finding our P and Q, we need to find two numbers that, when multiplied, give us the product of A and C, which is 1 times negative 40, resulting in negative 40. Simultaneously, these same two numbers must add up to our middle coefficient, B, which is 3. After checking the factors of negative 40, we find that 8 and negative 5 are our perfect pair. because 8 times -5 is -40, and 8 plus -5 equals 3. With these numbers in hand, we can split the middle term. We replace the 3x in our equation with 8x minus 5x. This gives us x squared plus 8x minus 5x minus 40 equals 0. Now we proceed to group and factor. Let's group the first two terms together and the last two terms together. This gives us the quantity x squared plus 8x minus the quantity 5x plus 40 equals 0. Notice that I've changed the sign inside the second bracket because I factored out a negative. Now, let's factor out the greatest common factor from each group. From the first group, we can factor out an x, leaving us with x times the quantity x plus 8. From the second group, we factor out a -5, which leaves us with -5 times the quantity x plus 8. Finally, we arrive at our final factorization. Since both terms now share the common binomial factor of x plus 8, we can extract it, leaving us with the product of two linear factors. The quantity x minus 5 multiplied by the quantity x plus 8, all equal to 0. As we will see in the next slide, it is vital to be careful with those negative signs during this grouping stage. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the logic we discussed in the previous slides, it is very easy to make small errors that can lead to the wrong answer. First, let's talk about sign errors. This is perhaps the most frequent mistake I see. When you are looking at the constant term, which we call c, please do not ignore its sign. If c is negative, remember that this dictates the signs of your two numbers, p and q specifically. One of your split numbers must be negative and the other must be positive. If you forget this, your entire factorization will be incorrect. Second, watch out for incorrect pairs. It is quite tempting to find two numbers that add up to the coefficient b and stop there. However, as we learned in our step-by-step approach, you must also ensure that these same two numbers multiply to equal a times c. Never settle for just the sum. Always verify both conditions to be absolutely certain. Finally, pay close attention to grouping errors, especially when dealing with negative signs. If you look back at our second example with the garden, you'll notice that when we factored out a -5 from the second group, the sign inside the bracket changed. Specifically, -5x minus 40 becomes -5 times the quantity x plus 8. It does not become -5 times the quantity x minus 8. This subtle change is crucial for the final step, where we extract the common binomial. Keep these points in mind as we move into our final summary of the lesson. Key takeaways. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of the method of factorization. First, let's revisit our main objective. The entire goal of this process is to take a quadratic trinomial, that's our three-term expression, and convert it into a product of two simpler, linear binomials. Essentially, we are breaking a complex expression down into much more manageable pieces. Now, if you remember nothing else from today, remember the golden rule. This is the heart of the splitting the middle term technique. You must find two specific numbers, let's call them p and q, that satisfy two simultaneous conditions. First, when you add p and q, the sum must equal the coefficient of the middle term, which we call b second. When you multiply p and q, the product must equal the product of the coefficient a and the constant term c. If you find these two numbers correctly, the rest of the process will fall into place. To keep your work organized, try to follow this consistent process flow. Always start by ensuring your equation is in standard form. Then, split that middle term using your two numbers, proceed to group your terms into pairs, and finally, extract the common binomial factor. Following these steps systematically will prevent you from getting lost in the algebra. Finally, I want to leave you with a tip for self-correction: verification. One of the best things about factorization is that you don't have to wonder if you got the right answer. You can always check your work by multiplying your two resulting binomials back together using the distributive property. If you expand them and arrive back at your original quadratic equation, you can be 100% confident that your factorization is correct. Keep practicing these steps, and soon this method will become second nature to you.